again, these two are in series with the entire vehicle load. So if they do quit, you stop charging the battery. Okay. So why not just keep using mechanical regulators? I mean, they used them for years. I mean, why not keep doing it? Okay. Performance all right, but it could be better. As these cars go into the realm of not daily drivers, of fun cars, they tend to sit over the winter, so they'll hang up. Okay, if they're not used for a long time, so you'll start the car up after not driving it for a month or two, and either you'll have to polarize it again, or or the contacts will stick. So all of a sudden you try to drive the car and you'll discover, Jesus, you know, my battery's dead when I'm halfway there.
Or overcharging.
Or overcharging. That's exactly right. Or can overcharge, can cook your battery. Okay. The other thing is, and I don't have any proof of this, but I really believe that they're declining in quality. You know, in the 40s and the 50s, Ford, Chevy, Plymouth, MG, you know, everybody bought these things. Okay, and there were people who competed to make them. There were people who knew how to make them. There were people who specialized in this. That was their product. Okay, that's not the case anymore. Okay, even garden tractors don't use them anymore. They use electronic ones. So all those designers have all gone fishing. Okay, and all the suppliers are not making them anymore. So the ones that you tend to get today are made by Happy Smiling Dragon Corporation or some other third-tier kind of people that are not going to be selling them on the basis of their quality. They're going to be selling on the basis of their low price. Okay, so I think that we're sort of at the end of where we can expect mechanical regulators to be in use. So, here's the electronic voltage regulator. It's kind of hard to see in this light, but this is what Tony and I came up with. And it looks complicated, but it does exactly the same three things that the other one does. Okay. So the first one is the voltage regulator section. Okay. And the way it works is that the field is out here. The field is between these two terminals, and this is the armature output, okay, that feeds through to the battery over on this side. So what happens is, this is a control element, this little block here. Has a very, very precise 2.5 volt reference in there that's within a couple of tenths of percent and drifts only a couple of parts per million over a temperature range. So what happens is we compare this voltage, sample this voltage, to this 2.5 volts in here, and through the magic of these transistors, we then use these transistors to change the voltage going to the field coil. So this guy is much, much more accurate than the mechanical relays would be, because it's designed to be extremely accurate. Okay, it can hold within parts per million, whereas the other the mechanical guys would drift 5% with temperature, with time, with age. So that's not going to do that. Okay, so the overall control we're going to get is within 1 or 2%, whereas before we were at 5%. Okay, so that's a big advantage. Okay, so then the current limiter. Okay, the current limiter here is over here. Excuse me. What happens is there's a very tiny resistor over here, 1 milliohm, 1,000th of an ohm, and we monitor the voltage drop in here, and we use that. If that goes higher than the value we want to see coming out of the generator that's over here, we use this to turn the loop off. Okay, so that's very accurate also. That's probably within 3 or 4% we can get that. And Tony will tell you, this is like a brick wall. Okay, you can see the way you get it is if you idle the car, turn the lights on, okay, turn the lights back off again, and then bring the RPM up. It would say, I need to charge the battery. The battery went flat on me. Okay, I need more than 20. In Tony's case, it's 22 amps. I need more than 22 amps, okay, to charge the battery back up again. That went a little bit flat from my previous usage, but it just won't do it. If you look on the ammeter, it just gets to 22 amps and it just stops. Okay, it can't go beyond there. So that's a big advantage. This works much more accurately than the mechanical ones, and it's not going to change with time. So I can go with that. And finally, the disconnect. This guy here, again, hard to see, but there's a transistor here that only allows a current to flow in one direction. Okay, current can only flow from the generator to the battery out here. It can't go from the battery back. Okay, that's a real specialized thing called an ideal lossless diode. Okay, a lot of commercial units just use a diode. Okay, they can put a diode in there, and that's very simple. But at 22 amps, if you get half a volt or 6/10 of a volt, that's 13 watts lost, which is going to get the PC board very hot. So this part here that my company makes, just so happens, controls the field effect transistor that's in there. For instead of 6/10 of a volt drop, it has 25 millivolts of drop. So it's about 1/25. So then we're losing about half a watt at the most. So what are the advantages of the electronic regulator? Much more precise, initial tolerance, no aging, and temperature stability is much better. And it doesn't wear out. Okay, this guy's going to be the same in 5 years as it is today. It's not, you know, none of those parts that are in there have any kind of drift mechanism to them where they're going to change. So if you got advantages, you're going to have disadvantages. That's the way it works, right? So what are the disadvantages? Well, the disadvantages are that it's susceptible to over voltage, over current, or over temperature destruction. You guys know this, but let the magic smoke out of them, okay? So what do? We designed the thing very conservatively for the application to keep these things from happening. All the parts here are rated for continuous operation to greater than 36 volts, okay? All the parts that we use inside are rated for greater than 36 volts. And, you know, we have a 12-volt system in the car, but we can get spikes and transits to go to higher than that. So we have voltage protection that limits the exposure to 24 volts at the maximum. So we're at only 2/3 of the maximum rating, the maximum voltage rating. So we're good there. The 22 amp version is running at about 1/3 the short-term current capability. We could probably put out about 50 or 60 amps for a few seconds with the device without blowing it up. So we're well below the current threshold, and the temperature ratings of all the parts that matter are minus 40 to plus 105 degrees C. So we're not going to over temperature them, and we're short circuit protected. Okay, so that mitigates those devices now, or mitigates those disadvantages. We've only begun to test them actually in a car, okay? So that's obviously the proof of the pudding is what do they do when we actually put them in the car, and we're going to have to log some hours. Tony has how many miles?
Well, I've been running it for a year, and I've had, you know, 5 or 6 hours of running continuously with the with all power pulling, so it's maxed out on the generator, and nothing melted.
Yeah, so far, we haven't found anything yet, but of course, you know, something like this bears more testing, okay? Now, the other disadvantage is that there is a current draw with the key off, okay? It's about 2 milliamps, all right, 2007 amp. And that's less than the battery self-discharge. Now, we could have made this lower. We could have put more parts in there to make it lower. We could have brought that down into the microamp range. But you're already less than a battery self-discharge, so the truth is, long-term storage, you need a battery tender. It's not going to, the battery tender is not even going to notice that that's in there. So that part, we decided that we wouldn't change anything else.
And it's a lot less draw than a modern car on its battery.
Well, that's a good point. That's right. A modern car might be as much as 50 milliamps.
Does the old-fashioned car have any draw with the key off?
Essentially none. No. It would be, I mean, assuming you didn't add an alarm or something like that, but just like a stock TR4, for all practical purposes, just be some leakages, you know, way less than that number. I'm sure it might be 10 times less or 100 times less than that number.
Do you have to be careful with jump starting or something like that?
No, the part should be fine for jump starting. Again, it's protected at 24 volts, and nothing, unless you get inside the circuit board, nothing you can touch on the outside will make the inside go above 24 volts. Okay, and all those parts are rated for 36 volts, so that's okay. That's a good question. Okay, now I would not do what some people do in the Great Lakes region. You know, when you've gone ice fishing for 3 days and they bring the tow truck out, and that's put 24 volts on a 12-volt car, okay, I would not do that, okay. Big trucks, they hook up to arc welders, so they're even worse, okay, but it's not really designed for that, okay. It could probably take a few seconds of it, but if you did it for a long time, you'd probably blow the device up. You'd probably blow lots of things up, true, but it probably wouldn't do that. So, all right, so that all sounds great. So Tony has the first unit that's in use now, excellent results. Second unit's going to go to Dave Hutchinson. I don't think it has yet.
No, he hasn't given me his
his core. Yeah, his core.
I have his circuit board.
We're going to pass around the circuit board in a minute. Okay. So now availability. So there's the real question. Okay. So far it's a science project. Okay. You know, we've done it because it was fun. Okay. And the parts to make it, I think we figured out came to about 150 bucks in low quantities. Because an electronic,
well, at absolute most.
Okay, so well, let's say 150. Okay, because on electronic components, they kill you at single units, but none of us is willing to put out the money to buy the parts to make 100 of these yet. Okay, we could probably get it below $100 if we made 100 or so of them. Okay. But the biggest stumbling block, we think we have a good design. The biggest stumbling block on this is the enclosure. Does it have to look like a stock regulator? Okay. Can we put it in a little box of some sort? And that's the part that's kind of churning still at this point. Okay. You know, Tony essentially took a bad regulator and yanked the stuff out of it and put it inside. So his looks like a stock regulator on the outside. But doing that's not really something you could do more than on a hobby basis, you know. It probably would be very difficult.
It's extremely time consuming.
Yeah, so it's not something you could build and sell and even make McDonald's wages back to sell them to other people. You know, like I say, right now it's just a science experiment.